Let's look at the capital asset pricing model. Capital asset pricing model, CAPM. So in the capital asset pricing model, we have a very special portfolio called the market portfolio. So M will be our market portfolio. Then every return on asset I will be alpha I plus beta I Rm plus epsilon I. And these different things, this is the return on asset I. Alpha is the drift. This term here with the beta, this is called the systemic risk. And epsilon is the diversifiable risk. So in this model, the returns on an asset are some asset-specific drift, some systemic risk that varies along with the entire market, and then some randomness on top of the returns that is diversifiable, which means if we own lots of assets, these should cancel. These are all just random noise. So how do you find the betas? So beta is the covariance of the return with the market return over the variance of the market return. And so this is the model here. We have a definition for finding the betas, and then we have a formula for the returns on every asset. So what is covariance and variance? Let's jog our memory here. So covariance of Ri Rm equals the expected value of Ri Rm minus the product of the expected values. So it's the expected value of the product minus the product of the expected values. And we can do a little example here. So suppose that Ri and Rm are totally independent. What does that mean? If Ri and Rm are totally independent, then the expected value of the product equals the product of the expected values. And that means when we subtract these, we just get 0. Equals 0. And so beta, in this case, will be 0. So independent assets that are totally independent of the market will have a beta of 0. What about if we have identical? So identical assets, if we're investing in the entire market with one asset somehow, what happens? Then we have the expected value of Rm times Rm minus expected value of Rm, expected value of Rm. And that's expected value of Rm squared minus the expected value of Rm squared. And this is the definition of variance. And so in this case, we'll get a beta of exactly 1. So if you have an asset that exactly mimics the market, it'll have a beta of 1. All right. What is the expected return of our asset? So we have a formula for the return. What's the expected return? That's a slightly different question. So just putting an expectation on Ri, we'll call that mu I, and that'll be alpha I plus beta I times the expected value Rm plus the expected value of epsilon I. And then this is 0 because this is noise. Then this we'll call mu m. And so we have mu I equals alpha I plus beta I mu m. If I can draw mu's. All right, so this is the expected return of asset I is related to the expected return of the market and alpha and beta. And if you can do a similar calculation and get the standard deviation of return, and that'll end up being beta I squared sigma m squared plus EI squared. And so sigma m is the standard deviation of returns of the market, and EI is the standard deviation of, well, I'll say EI squared is the variance of epsilon I. All right, so here's formulas for the expected return and then the deviation of our expected return. Now, what about if we have a portfolio? So now we have a portfolio pi, and we want to get the return on pi, so that'll be some delta over the portfolio. This will be our return. What's that going to be? We're going to have some weights for every asset, so it'll be the sum from I from 1 to n, Wi, Ri. So we're just weighting all the assets we hold in our portfolio. And we can expand this Ri out. So this will be the sum Wi alpha I plus the sum of the Wi beta I Rm plus the sum of the Wi epsilon I. Okay, that's just substituting in the definition of Ri. Now we can go the expected return. So what's the expected return of our portfolio? This will be, we'll give that a name. We'll call that mu of pi. So this will be the sum of the Wi alpha i's. And now this term Rm is constant, so we can take this out, put that over here. And we're doing an expectation, and the expected value of the return on the market was mu m. And we get the sum Wi beta I. And then here, the expected value of the sigmas goes to 0, or the epsilons goes to 0. All right, and now we can say let alpha pi equal this weighted sum here, the Wi alpha i's, and beta pi is the sum of the Wi beta i's. Now we have a nice formula here. So this mu pi is what? It's just alpha pi plus mu m beta pi. That's it. So here's our portfolio return. All right, so this is pretty cool. So what we've done is under CAPM, capital asset pricing model, every return has a drift, a systemic risk, and a diversifiable risk. And alphas and betas indicate the drift and the systemic risk. And we have a formula for beta here. We went through and did math and figured out the expected return on each asset. And then if we hold a whole portfolio with different weights of every asset, we went through and did the math, and we figured out the expected return of our entire portfolio only depends on the weighted final alpha and beta of our portfolio. So this means by just knowing the alphas and betas of all our assets, we can figure out the return of our portfolio. And you can do similar math to this and get calculate the standard deviation of return too. And so that'll be some other formula. And by knowing just the alphas and betas of every asset, we can figure out the optimal risk-return trade-off for our portfolio. So that's the capital asset pricing model. Pretty cool.